Hi. Okay, so this is part two of the first ionization energies. So we know that. Okay, so we know that the first ionization energy decreases down a group. So as we go down a group, right, the first ionization decreases. This is because as you go down the group, the electron being removed is further from the nucleus because there's more shells and there is more shielding. Therefore, the nuclear attraction is less and less energy is needed to remove the outer electron. Okay? Across a period, so sorry. No, before I come into across a period, it's important to note that successive ionization energies. So, successive ionization energies of sodium, right? So the first electron takes 496 joules, and the second one, a massive jump of 4,563 joules. That's loads more energy. Then it increases, blah blah blah. And then basically, to remove every single bloody electron from sodium, it will take 159,000 kilojoules per mole. That is a crazy amount of energy, yeah. So that just shows how strong the bonds are. So basically, this suggests that one electron furthest away from the positive nucleus is easy to remove. 8 electrons near in the nucleus are hard to remove. So 2 electrons are very close to the nucleus because they are near to a positive charge. Right? So this is the successive ionization energies of sodium. As you can see, it's a linear trend, and we can see that it takes the more electrons removed, the higher energy it requires. So now we're going to come across ionization energies across a period. So this is a graph to show the successive ionization energies across a period. So we're going, and this is for the first 20 elements. So H to He, and then this is a period now. So L, lithium to beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So that's the same as going along here, right? So, right, okay. So now, generally, there is a general increase as we go up across the period. However, we can see these little blips, blip in oxygen and a blip in boron, and in the third period we can see there's a blip in magnesium, a bit of a weird one here, and then a massive blip, right? Okay, so in general terms, there is a general increase in first ionization across a period. This is because the electron being removed is in the same shell, because obviously as we're going across the period, they're in the same shell, innit? They've got similar shielding, but because there's more protons in the nucleus, there's going to be a stronger nuclear attraction and more energy is needed then. So and also to note, the atomic radius decreases as the attraction from the nucleus increases. Okay? So, now we're going to explain the dips now. So, the dips. Okay, so explaining the dip now. There is a small dip in first ionization energy between the group 2 and group 3 elements from Be to B. Okay? So as we can see, so as we're going across the period, right? Similar shell, similar shielding, but we're going from beryllium, which is in group 2, and we're going to boron, which is in group 3. And the reason for this is because in beryllium, the electron configuration is 1s2, 2s2, and we can see this, we can remember this from our previous videos because this is in the S, so S, P, D, S, that's 1, that's 2, so it's going to be 2s2, right? And then in boron, it's 1s2, 2s2, 2p1, and obviously this makes sense because we're adding one more electron, we're in a new sub-level, which is p, right? So the electron being removed in boron is in a 2p subshell with it, which is further from the nucleus than the Be2s electron. Therefore, the nuclear attraction is less and less energy is needed. So, and for the third example, there is a small dip in first ionization energy between nitrogen and oxygen, so between these two bad boys, and between phosphorus and sulfur, these two. So, nitrogen, that's nitrogen there, oxygen. So as we can see, the difference is that in nitrogen there's a 2p3, oxygen there's a 2p4. Oxygen has a paired electron in one of its orbitals. This basically leads to a repulsion. So because there's because they're more repulsed, because there's a repulsion, less energy will be required. So we can see this because there's a dip in first ionization energy, because obviously there's less energy required because of the repulsion, because they're in the same orbital now in oxygen. Alright, hope that makes sense. And then between the end of one period and the start of the next, there is a big drop in first ionization energy. So the end of one period, so the end of neon, we're going from the end of neon, beginning sodium, right? So from Ne to Na, it goes 1s2, 2s2, 2p6, and then Na is 1s2, 2s2, 2p6, 3s2. So the difference is this new 3s orbital. And the reason for this is because the electron being removed in sodium is in a new shell, which is this, further from the nucleus, and with more shielding, so therefore the nuclear attraction is less and less energy is needed. So henceforth, there is an absolute huge drop. All that less energy is needed. Okay? And then we talked about the successive ionization energies, so that's that. So in the successive ionization energies, the electrons move from a more positive ion, so more energy is needed. Bigger increase in ionization energy. Right, we know that. Patterns, general increases in ionization energy. Right, so the ionization energies are increasing in roughly equal steps. The electrons are being removed in the same shell. If there is a big difference in successive ionization energies, the electrons are being removed in different shells. Okay? So, another graph there. Oh, sorry, this is down a group now. And you can see that the ionization decreases dramatically. This is down the shell, but down a group, sorry, between the periodic table. And you can see how the energy decreases a lot, because as we're going from beryllium to magnesium to calcium to strontium to barium, as you can see, we're going down. So this means that there's more and more shielding, which means as there's more shielding, there's less attraction from the nucleus to the outer electrons because of the extra shielding, and this causes a decrease in first ionization energy. Okay, I hope that helps. We have now finished 3.1.1.3 electron configuration, because we're going to give this a quick overview now. So, explain how first and successive ionization. Okay, we know this because of the big dips and the big gaps, and remember we just said that here that it's like evidence. It's evidence, provides evidence. This is very important here. So like it provides evidence for the existence of energy levels, right? That is very important. Provides evidence because of the blips, like especially these blips here that we have. So like between sodium and magnesium, between sodium and magnesium, we're going. One second. So like I was saying, between sodium and magnesium, if we look at the graph here, there's a dip. So we can see that sodium requires less energy than magnesium, and this is because of the it's the repulsion. Yes. So basically, in magnesium, the two electrons in that little s orbital there, they're going to be repelled more. So therefore, there's going to be less energy required in Mg. No. Basically, oh god.